Hello friends, myself Dr. Nandakumar Raubole from College of Engineering Ambazugai is going to deal with numerical methods in mechanical engineering. This is our 7th lecture. In previous lecture we have discussed about the numericals to find the root of an equation using bisection method. Now today we are going to discuss the Newton Raphson method and the numericals to find the roots of a equation. So this method, which is known as Newton Raphson method, is used generally to improve the results obtained by one of the previous methods, bracketing methods. This is not a bracketing method. So in bracketing method, the two approximations which yield function value once as positive, once and as negative is used. But here this is not a bracketing method, this is an open method. Only one approximation is used, and that approximation is refined step by step. Now let us consider, let this x naught be an approximate root of function f of x that leads to 0, and let x1 is the correct root or exact root, and which is equal to x naught plus of h. That means this is x naught be an approximate root. This is approximate, not a correct answer or correct root, and that yields f of x as 0. And let this is a revised root or a new approximation x1, which is equal to x naught plus h, which is correct root. We call this as a correct root, be the correct root. So that function f of x1 leads to 0. So expanding f of x naught plus h by Taylor series, we get f of x naught plus h as f of x naught plus of h f dash of x naught plus h square divided by 2 factorial f double dash of x naught plus, and which is equal to 0. So neglecting the second and higher order derivatives, neglecting the second order and higher order, derivatives, we can write this function as f of x naught plus of h f dash of x naught, which is equal to 0. On simplification, f of x naught is equal to minus h of f dash of x naught, transferring second term on right hand side, we get this as h is equal to minus of f of x naught divided by f dash of x naught. So we call this as equation number 1. So now already what we have assumed is x1 is equal to x0 plus h. This is say equation number 2. Now we have obtained h as f of x0 minus f of x0 divided by f dash of x0. So this is equation number 1. So substituting equation number 1 in this equation number 2, we get x1 is equal to x0 minus of f of x0 divided by f dash of x0. So we call this as equation number 3. That is nothing but a revised root of equation x1 can be obtained as the previous approximation minus of the function value at previous approximation divided by derivative of the function at previous approximation gives us a revised approximation. Therefore, in general, if we say the n plus 1th approximation can be obtained by xn minus of f of xn divided by f dash of xn. In general, we can write, so if we know xnth approximation, then xn plus 1 approximation can be obtained by knowing the derivative. So successive approximations such as x2, x3 and so on, xn plus 1 can be obtained by this equation number 4. So if we know any approximation, the improved approximation can be obtained by this Newton's Raphson method. So now we will see how to use this Newton Raphson method to improve the existing root of a equation, or we can find out root of equation. So now let us consider one numerical. Use Newton Raphson method to find out root of equation f of x is equal to x to the power of 3 minus 2x minus 5. Here approximation is not given, no approximation is given, so we assume for solution purpose, if approximation is given, that is well and good. If not given, then we can assume some value. Say here we assume approximation x0. Assuming approximation as x0 is equal to 2. First we are going to assume x0 is equal to 2. So now we want to find out a root of this equation. So first we will prepare a table. What is this table? Xn means first approximation, which we are going to assume as 2. Then f of xn, function value at this 2. So here function, what is this function is f of x is equal to x cube minus 2x minus 5. Now we are going to take x value as 2. So substituting 2, f of 2 we get as 2 to the power of 3 minus 2 into 2 minus 5. So this results into 8 minus 4 minus 5. 4 minus 5 minus 4 minus 5, 9 minus 9 plus 8 means this will be minus 1. This will be minus 1. F of 2 is minus 1. So now differentiating this function f of x, we get f dash of x, and that is 3x square minus 2. F dash of 2, if we substitute here 2 into 2 square minus of 2. So here 2 square is 4 into 2 is 8. 8 minus 2 is, this is 6. Sorry, 4 into 3, this is 3. 12 minus 2 is 10. So this is f dash of 2 is 10 and f of 2 is minus 1. So substituting this in this table, f of 2 is minus 1 and f dash of n is 10. Now we want to find out revised approximation. So revised approximation is given by x1 is equal to x0 minus of f of x0 divided by f dash of x0. So x0 value is 2. We assumed x0 as 2. So assuming this x0 as 2, we have started. So we write 2 minus of f dash of f of 2 is minus 1 minus of minus 1 whole divided by 10. So this works out to be 2.1. 2.1 is new approximation. So new approximation we can substitute here as 2.1. Now approximate error we cannot find out. We cannot find out true error because true value of root is not known. So in this problem it is not given what is the value of x of t, or true value is not known. Therefore we cannot find out true error. So true error is also dash. Now coming to this next step. So this was old approximation which we assumed as 2. Now new approximation is with us, that is 2.1. So what we have assumed answer is 2. Now this method says that this answer 2 is wrong, this 2.1 is correct. Now we take new approximation as 2.1. Now if we substitute 2.1 in this function, f of 2.1 which is equal to 2.1 to the power of 3 minus 2 into 2.1 minus 5, then we get f of 2.1 as 0.061 and f dash of 2.1 we get f dash of 2.1 3 into 2.1 square minus 2. So f dash of 2.1 we get here as 11.23. So f of 2.1 and f dash of 2.1 we got like this. We substitute this in this table. F of 2.1 is 0.061 and f dash of x is 11.23. Now we want to find out again revised value of this x. So revised value can be obtained again as in place of x0 it is x is equal to 2.1 minus of f of x0 is 0.061 divided by 11.23. So this works out as 2.094568. The new value of x is 2.094568. So we can substitute this as the revised approximation is 2.094568. Now this approximate error we can find out. So approximate error can be obtained. So approximate error is nothing but previous approximation, and we know new approximation. Previous approximation minus new approximation divided by new approximation or revised approximation. Previous approximation was 2.1, new approximation is 2.094568 divided by 2.094568 into 100. So if we find this is nothing but equal to 0.25%. So 0.25% is the error, approximate error, 0.25%. But we can't find out true error because we don't know true value of a root of this function. So if we know true root, then we can find out true error, otherwise true error cannot be obtained. So now this is the revised answer which takes this place, that is 2.094568. Now to get this function value f of x, if we come here, f of x is equal to x to the power of 3 minus 2x minus 5. So f of x value we are going to substitute as 2.094568, which is equal to 2.094568 to the power of 3 minus 2 into 2.094568 minus 5. So on simplification, this gives us 0.0018. Then f dash of x, which is nothing but 3x square minus 2. So f dash of this function 2.094568, revised approximation, that is 3 into 2.094568 square minus 2. So on simplification, this results as 11.161453. So this is new function. So a revised approximation xn is nothing but old approximation, which was 2.094568 minus of f of x is 0.0018 divided by 11.16453. So this formula we are using, xn is equal to x naught minus of f of x naught divided by f dash of x naught. Now in place of x naught we have 2.094568. So now on simplification we get this as 2.0945518733. So now this is the value. We can substitute it in this table. So by substituting this value in function, we get this as 0.00018 function value, and derivative of that function is 11.161,453, and revised value of approximation we are going to get as 2.09455187. Now we can get approximate error here. Approximate error we can find. Approximate error is equal to previous function value and revised function, sorry, a revised root of function, that is previous approximation and revised approximation we know. So here a revised approximation is a bit smaller, so we take previous approximation first, 2.094568 minus revised approximation is 2.0945518733. 453, this is revised approximation. So divided by revised approximation 2.0945418733 into 100. So this approximate error works out to be 0.0007%. So approximate error we can write here 0.0007%, and true error we cannot find out. So this approximate error has considerably reduced, so we can stop here, and the answer or a root of this function is known to us. Therefore we can write answer as the root of function f of x is equal to x to the power of 3 minus 2x minus 5 is 2.094551871833453 with approximate relative error as 0.0007%. This is how we are going to write this answer. So now we will consider one more numerical on this Newton Raphson method. So this is second numerical. Find a root of transcendental function f of x such that the true error is below 0.5% using Newton Raphson method, approximate root of which is 1, and true value of function or true root of function is this. X of t is given. This is nothing but x of t, true root is given. So here we can find out true error. So before finding true error, we have to differentiate this function f of x. F dash of x is equal to, so this is product of two parts. So here we can write first function as it is, derivative of second function as e to the power of x, derivative of e to the power of x is e to the power of x plus, and second function as it is, derivative of first part is x, derivative of x is 1, and derivative of minus 1 is 0. So this can be written as x plus 1 into e to the power of x is the differentiation of function. So this, after differentiating, we get this as the derivative. We call this as equation number 2, this we call as equation number 1. So now we want to find out the root of this function, but he has given first approximation. In previous problem, approximation was not given. There we assumed x is equal to 2. Here already it is given that approximate root of this function is 1. So first approximation itself is given. So here we have to start with xn as 1. So now we can find out, see, this is f of x is equal to x e to the power of x minus 1 and f dash of x is equal to x plus 1 into e to the power of x. So now x value we are going to substitute as 1. So f of 1, if we substitute, so this is 1 into e to the power of 1 minus 1. So this gives us as 1.71, and f dash of 1 is equal to 1 plus 1 e to the power of 1. So this gives us f dash of xn as 5.43. So now we can find out new root or revised approximation as x naught minus of f of x naught divided by f dash of x naught. So x naught value, so previous approximation is 1, or x naught is taken as 1. 1 minus of f of x is 1.71 divided by f dash of x naught is 5.43, which is equal to the revised root of this is 0.68. So we can substitute it in this f. If we substitute this in function, that is x e to the power of x minus 1, which is function f of x, So by substituting one this in this, we get this as 1.71, and derivative of this is x plus 1 e to the power of x. Substituting 1 in this, we get this as 5.43, and this f of x n plus 1, we write this as x naught minus of f of x divided by f dash of x. So this gives us as 0.68, and approximate error we cannot find out because previous approximation we don't know. So true error we can find out. True error is nothing but, we will find out true error somewhere here. True error is equal to true value we know, true function value is given, and approximate value is known. So approximate is 0.68, and true value which is given in this problem is 0.56738281, to whole divided by true value of root is 0.567382812 into 100. So on simplification, this gives us true error as 19.84%. So true error is obtained 19.84%. 19.84. So this is a revised root of this function. So we take this 0.68 as once again revised root. Now we again find out function value. So f of 0.68 we find out. Revised value of x naught is now 0.68. So if we substitute 0.68 e to the power of 0.68 minus 1. So on simplification, f of 0.68 gives us 0.3422 then f dash of 0.68. So if we substitute as 0.68 plus 1 e to the power of 0.68 on simplification, this yields as 3.316 11459. Now this xn is equal to x naught value now is 0.68 minus of f of x value is 0.3422368. So this f of x naught now, this is the value, and f dash of x naught value is this one. So divided by 3.31611,459. So revised value of this root we get as 0.582787. So we substitute these values in this table. On substitution of 0.68 in this function, we get this function as function value as 0.3422368, and on substituting this x value in this derivative of this function in place of x 0.68, we get this as 3.31611,459, and a revised value of this root we get as 0.582787. Now we can find out approximate error and true error. So first approximation we know, revised approximation we know. So to find out approximate error is equal to, previous approximation was 0.68 and revised approximation which we obtained is 0.582787 divided by 0.582787 into 100. So this gives us approximate error as 16.68%. This is approximate error. Then true error we want to find out. True value we know. True value is given as 0.5673 and this approximation is 0.58. So 0.582787 minus of true value of this root is 0.567382 whole divided by, again true value is 0.567382812 into 100. So on simplification, true error works out as 2.714%. So we substitute this approximate error and true error in this table. So approximate error is 16.68% and true error is 2.714%. Now this is a revised approximation which we have obtained. Now old approximation is replaced by revised approximation, that is 0.582787. On simplification of this value of x in this function, we get the function is f of x is equal to x e to the power of x minus 1. X value we are going to take as f of 0.582787. So this we get as 0.582787 into e to the power of 0.582787 minus 1. So on simplification we get this as 0.0437849 and f dash of x, which after differentiation we got as x plus 1 e to the power of x. So here f dash of 0.582787, which is equal to 0.582787 plus of 1 e to the power of again 0.582787. On simplification this leads to be 2.834808 and xn plus 1 is equal to x naught plus of minus of f of x naught divided by f dash of x naught. So x naught value which is taken as 0.582787 minus of function value at this is 0.0437849, which we have obtained here, f of x, and f dash of x we have obtained here. So in denominator 2.834808. So on simplification this yields to be 0.567341. So now we substitute this first value, second value and third value in the table. So revised approximation xn plus 1 is nothing but 0.56. So we substitute these values. So on substituting this revised approximation in this function x e to the power of x minus 1, it results as 0.04 37849, and on substitution of this in this derivative we get this as 2.834808, and on substitution of these all three in this equation, x naught minus of f of x divided by f dash of x naught, for revised approximation we get as 5 point, sorry, 0.5.567.341. Now we take approximate error. So previous approximation was 0.58. Now revised approximation is 0.56. So we find out approximate error. Approximate error as 0.582787 minus revised approximation which we obtained recently now is 0.567341 whole divided by 0.567341 into 100. So this results as 2.72% as the approximate error. Now true error we can find out. True error is equal to true value we know, which is 0.567382.812, and revised approximation which we have obtained is 0.567341 divided by true approximation or true root is 0.567382812 into 100. So true error becomes 0.007%, which is less than 0.5%. So coming back to this table, here we can write approximate error is 2.72%, whereas true error is 0.007%. So this has reduced considerably. Therefore, we can stop here, and this we can call as the root of equation. So answer we can write as the root of function f of x is equal to x e to the power of x minus 1 is 0.567341 with approximate error as 2.72% and true error as 0.007%. So this is the answer, where the root of given equation is 0.56. So what was suggested, x is equal to 1. So initially what he is suggesting, the root of this function f of x is close to 1. So it is close to 1, but it is not exactly 1. Means this is the root, but it has got a error. So this error is reduced to 0.007%, and the now revised root which we have obtained is 0.567341, and which is not equal to the true root of this function, because it has got the still error. So still we have opportunity to improve this answer, and we can proceed further to improve this answer by repeating these iterations, so that this error can still be reduced. So there is a scope of reducing these errors in next iteration. So but we are going to stop here, as the error true error has reduced to below 0.5%, so which is a very small error. So this can be accepted as the root of equation. So we stop here, and few more numericals we will be solving on the Newton Raphson method in next lecture. Thank you.